Sketch a graph of each function. Label all zeros and the coordinates of all maximum and minimum points. That's a little ridiculous. I'm not going to ask you to do that much. I may ask you to find the zeros for sure, and then give a general sketch of what the graph looks like. But I probably won't ask you to label the coordinates of the maxes and mins. But can you take a look at something like f here and at least find the zeros? It's 2x to the fifth minus 3x to the fourth minus 11x cubed plus 14x squared plus 12x minus 8. How many zeros would you anticipate for this fifth degree function? 5. If it doesn't have 5, it's possible then that some of them are imaginary. But we'll find out. One thing to consider when you look at this, if it's a fifth degree function and the leading coefficient is positive, a is 2, degree is 5. Do you guys remember that little chart that we made that said if the degree is odd and a is positive, what should the general shape of the graph look like? Should it be or which one? If you said you're right. The general shape of this graph should be increasing from left to right. When it's an odd function and a is positive, it should be increasing. All right? So it's all about the roots and the factored form in order to find the x-intercepts. All right, so we're going to have to factor this bad boy. You ready? Well, where should we start? Good place to start. Want to take a peek? We'll take a peek on here and see where some of the solutions might be. Or you could use the rational root theorem. Rosemary, we talked about the rational root theorem and how you could test every point. Or you could just take a peek at it on here. So according to our graph, it looked like we had potential solutions at -2, -1, 0.5, and 2. And we thought 2 was a what? A double root. That means that it would be in a factor squared. Okay? It would be part of a factor that's squared. Boom, 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 boom. So those are the 4 roots that we think that there are, one of them being a double. I think it's going to slice up, down, up, and then bounce off at 2. So what I'm going to do is I'm going to take one of these solutions, all right, and see if it works in synthetic division. Let's take -2 and do synthetic division on it. Ready? Just to practice. How does synthetic division work now that we have -2 as one of the solutions? You take the coefficients, right? 2 from x to the fifth, -3 from x to the fourth, -11 from x cubed, 14. Let's get these guys out of here for a minute. -11, 14, 12, and -8. This is a pretty big synthetic division problem. A little -8 right there. Once we make the big line underneath, how does synthetic division get kicked off? What do you start with? Bring the 2 down. Multiply. What do you get up here? -4. Add. -7. Multiply. What do you get? 14. Add. 3. Multiply. -6. Add. 8. Multiply. -16. Add. -4. Multiply. 8. Add. 0. I made it to a remainder of 0. That means -2 is definitely one of the solutions. Since -2 is one of the solutions, we're going to switch to green here. Since it's one of the roots, what would its factor look like? X plus 2 or x minus 2? X plus 2 is definitely one of the factors. The other one is going to be populated with, well, this column started as x to the 5, right? 2x to the 5. Once you do synthetic division, it's now 2x to the 4th. Here's your synthetic division. You really need to pay attention. This column was x to the 4th. Now it's negative 7 x cubed. This is 3x squared. This is 8x and minus 4. So we have one factor and then this giant polynomial that we're still dealing with. We know we have another. We have some other roots that looked good, right? We thought that negative 1 looked like a potential root. So you know what you could do next? You could now do synthetic division on one of the other roots that we had, like negative 1, and these coefficients, 2, negative 7, 3, 8, and negative 4. And you can continue doing that until you have it in factored form. Was negative 1 definitely one of the roots when you look at your graph? You can press trace negative 1. Did it make 0? Check it. When you trace to negative 1. So negative 1, since we know it's one of the roots, should give us a remainder of what? 0. I'll let you play out the rest of the problem and get all of the roots if you like, if you want more practice on synthetic division. Ultimately, though, your final answer should be, well, you should be able to factor it, and the graph would have those 5, 1, 2, 3, 4, 5. There was a double there, single there, single there, single there. All right, so you have those roots. Once you get it in factored form, or even at the very beginning, if I plugged in 0, what do you get for the y-intercept? 0 would knock out this guy, this guy, this guy, this guy, this guy. What do you get? Negative 8. So another thing you could graph is its y-intercept down at negative 8. And then just give your graph a little sketch like that. For the purposes of this class, in this curriculum, 10th grade, Algebra 2, your graph is okay like that. Once you get to calculus, you'll be able to, and pre-calc, you'll be able to pinpoint these maximums, these minimums. Maximums, we know that's a minimum. And you'll also be able to pinpoint where this curve changes its inflection. Where does it switch from opening down to opening up? That's sort of what's coming next in your next career in math. But for now, find the roots and y-intercept. I'm happy with those. If you can at least do that.